This is Lab 5, Create Your Own Adventure. For this lab, the motion of an object that is dropped from rest and falls straight down was observed. After constructing a computational model based on the physics principle of Newton's second law, aka the momentum principle, the effect of gravity was observed. The model initially overpredicted the ending position of the falling flyer, which is the term used for the cheerleader being thrown in the air, by 0.139 meters, but after drag force was added, it was an extremely close model and the final predicted position was off by only 0.00047 meters. The video was recorded at 30 frames per second, as shown here. The height of the cheerleader was measured by using the height of the base, which is one of the two girls that is initially propelling the girl into the air, right down here, which was measured to be 1.626 meters, which was used to calibrate the length scales of the video. The coordinate system was used with the origin at the center of the cheerleader's uniform, or as close as possible center of mass of the cheerleader at the highest point of the stunt. The y-axis was aligned so that the object moved in the minus y direction as it fell. The video was slightly tilted, so the axis was tilted to reflect this. At each frame, the center mass of the object was determined by eye. The mass was estimated to be 41.73 grams. The object was blurry at points, but I made the best estimate possible. The computer model is based off of the fundamental principle of Newton's second law, which is shown here. The change in the velocity is non-zero at the point where the cheerleader's maximum height is reached and she begins falling downwards. That implies that the net force is not zero, so there is some interaction on the object. The first model is representative of simply the weight force on the object. Initial conditions were implemented for the cheerleader as the object. The mass of the cheerleader was inserted here. The initial position and velocity were both zero, since it is started from rest or as close to possible as rest in this scenario, and the origin is the chosen coordinate system. The time is also t equals 0. It was also made sure that delta t right here is small enough. The loop is the second law repeated until the ending time of 0.734 seconds. The total time is that of the time used of the cut segment of the video. Each equation is updated to reflect the equations v final equals v initial plus f net divided by mass times delta t. The weight force on the cheerleader was found to be the mass times the gravity times j hat, which is representative of the interaction of the Earth with the model. The observed position of the object was plotted against time. The object fell for a total of 0.734 seconds. When the first model was ran through VPython and was compared to the experimental data, you can see that the final position was slightly overpredicted as shown by the lines. The experimental results are shown in blue and the model is in red. This is due to the fact that the computer program does not account for any other forces. To obtain more accurate results, it is necessary to add a drag force, which is dependent on the properties of the object in question. In order to account for this force, this segment of code was shown right here. It is important to account for this drag force and the net force of the system to get accurate real-world results. This force was found to be negative b times the magnitude of the velocity times the velocity, which is shown down here and included at this point. This force, from here various b values were tested and the closest drag force was found to be 2.71. After finding this value, a much more accurate model was. You can see here that in the middle of the graph, the location of the flyer varies slightly. However, towards the end and at the beginning, they are very accurate and they end up at the same position when the drag force is included. The experimental data is shown in blue and the model position from VPython is shown in red. What the model is predicting can be represented by arrows. These arrows represent the vector forces. The change in the arrows show how the forces on the object behave in real-world observations, such as this flyer. This code was made here. The first arrow representing the weight force is constant size and points in the negative y direction. The arrow representing the drag force is not visible at the very beginning, but is seen and gets longer as time advances. The magnitude of the drag force depends on the speed. This new model is very accurate and predicts the final predicted position almost perfectly to the final observed position. The predictions towards the middle of the model are under-predicted as shown in the graph previously. This could have been caused by guessing of the weight, which was pretty close to an average weight of a flyer in cheerleading, and the overall video quality was slightly blurry at points. Also, it was significant that the cheerleader changed positions in the air, which is necessary when flying. However, it made it harder to track the exact center of the object. This application of physics to real-world life examples is extremely significant, especially in the case of cheerleading stunts. for both the safety of the bases, which are the girls holding the flyer, as well as the flyer. This all is taken into account when doing stunts. In order to reach the maximum height possible, there is a huge force going upwards, but the force coming down is also extremely important. The cheerleader that is flying has to be extremely aware of her surroundings as well as her body in order to maximize her drag force, in order to lighten her weight when being caught so she doesn't fall to the ground, and also in order to just have a safe execution, which gets points in cheerleading competitions. So this is all considered at the time during cheerleading. However, they don't necessarily think of it in such a physics manner. So overall, this lab provided a very accurate display of Newton's second law with a non-zero net force, specifically in the case of a cheerleading stunt. Thank you.